a rocky stretch of coast in Maine, August 1912. The locomotive lying on its side at the bottom of a shallow embankment is still partly steaming, and a crew of men is working to right it before the next high tide arrives. The accident happened at low speed on a sharp curve in conditions that the engineer should have been able to handle. The investigating officer from the railroad has spent the morning walking the track and has reached a conclusion that he will report in writing tomorrow. The rails on the outer side of the curve were 6 inches lower than the rails on the inner side, a configuration that should never have existed on a mainline railroad, and that was the direct cause of the derailment. This is the story of how the simple act of leveling the rails in a curve called superelevation took American railroads more than half a century to understand and standardize, and how the absence of proper superelevation was the cause of derailments that 19th century engineers often could not explain. A train passing through a curve is subject to centrifugal force that pushes it outward, away from the center of the curve. The faster the train and the sharper the curve, the greater the force. If the rails are level, the entire force is resisted by the flange of the outer wheel pressing against the inner face of the outer rail. The arrangement works at low speeds, but at higher speeds the force becomes large enough to either derail the train outward or to roll it over against the outer rail. The solution had been understood in principle since the early days of railroading, having been borrowed from the practice of banking horse race tracks. Raising the outer rail above the inner rail tilted the train inward, with gravity providing a counterforce that partially offset the centrifugal force outward. A properly superelevated curve allowed trains to pass through at speeds far higher than a flat curve could safely accommodate. The principle was simple, but the application proved difficult. The amount of superelevation required depends on the radius of the curve and the speed of the train. A train traveling at 50 miles per hour through a 1-degree curve requires less superelevation than a train traveling at the same speed through a 6-degree curve. A passenger train traveling at 60 miles per hour requires more superelevation than a freight train traveling at 30 miles per hour through the same curve. The optimal superelevation for any given curve, therefore, depends on the operating speed, and the operating speed depends on the type of traffic. Records from the major American roads of the late 19th century document confusion about how to balance these requirements, with different railroads adopting different formulas and different curves on the same railroad sometimes being superelevated inconsistently. The problem was made worse by the maintenance practices of the period. The track in a curve settled differently than the track on a tangent, with the outer rail tending to sink under the weight of trains, and the inner rail tending to rise as the ballast under it remained undisturbed. A curve that had been properly superelevated when laid would, after a year of traffic, often have its superelevation reduced or even reversed. Records from the maintenance of way departments document curves on which the outer rail was, in extreme cases, lower than the inner rail, a condition that no operating engineer of the period would have considered safe. The standardization came in stages. The Master Car Builders Association and later the American Railway Engineering Association developed standard tables relating curve radius, operating speed, and required superelevation. Federal regulation through the Interstate Commerce Commission and later the Federal Railroad Administration imposed minimum and maximum superelevation limits and required regular inspection of track geometry. Mechanical track geometry cars, developed through the 20th century, could measure superelevation continuously at operating speeds and produce records that maintenance crews could use to identify deviations from standard. The modern American mainline railroad operates on track that is, in the curves, superelevated to tolerances of fractions of an inch, maintained by inspection cycles that detect small deviations before they become operationally significant. The locomotive that derailed in Maine in 1912 would not have derailed in 2026. Not because the engineer would have been more careful, but because the track itself would have been built and maintained to a standard that the railroad of 1912 had not yet developed. The understanding of superelevation did not, by itself, eliminate curve-related derailments. But it gave the railroad something it had badly needed: a systematic relationship between the geometry of the track, the speed of the trains, and the safety of the operation, on which the high-speed running of the modern main line could finally be based.